Welcome to Demystifying Math. In this lesson, we're going to be finding the area between two polar graphs. We're going to use the equation 3 sine theta, which represents a circle in polar form. And we're also going to use the limacon, represented by 3 minus 3 sine theta. What we want to do is find the area of this small region here that's bounded by the two graphs. We're going to start by finding the point B. We can find the coordinates of point B because it's the intersection of the two graphs. So we'll just set the two equations equal to each other. Our first step, we're going to bring 3 sine theta over to the right side. So we have 3 equals 6 sine theta, or 1/2 equals sine theta. Then we're going to solve for the angle, which gives us pi over 6 and 5 pi over 6. Since we're looking for point B, which is in quadrant 1, we're going to use the pi over 6 for this case. So we're going to take pi over 6 and plug it into either one of the equations. Plugging it into either equation, you should get out 3/2 for your radius length. So that means that we have the ordered pair of 3/2 and pi over 6 as the coordinates of point B. What you should notice is that we did not get out the pole as an intersection point. Although the two graphs do intersect at the pole, they do it at different angles. So looking at the limacon 3 minus 3 sine theta, if we plug in pi over 2 for theta, we get out 0, which means that we have a point at the pole when the angle measure is pi over 2. For 3 sine theta, if we plug in 0, we get out 0. So the point at the pole is when the angle measure is 0. So they do have points at the pole, but at different angles. Alright, the next thing that we're going to do is figure out which angle measures we need to use in order to find this area when we integrate. Okay, so what I'm going to do is take a point that is on the circle, and I'm going to move it around the circle, which means I'm actually changing the angle measure of that point. And as I do, it's kind of filling in an area, a part of that region that we're concerned about. Now notice that I'm stopping at around pi over 6. And I'm stopping there because if I went further, I'd be filling in area that is not inside the limacon. So we want it to be bounded by both figures. Now what we're going to do is do the same thing, but move a point along the limacon. Okay, so for this one, what we're going to do is start around pi over 6 and move it around toward pi over 2. And as we do that, we're going to fill in the rest of that shaded region. So really what we need to do is integrate for the circle from 0 to pi over 6, and then for the limacon from pi over 6 to pi over 2. Okay, so the area formula for polar graphs that we're going to use is 1/2 the equation squared d theta, and then our endpoints of integration. So since we really have two different integrations we have to do, what we're going to do is integrate the circle from 0 to pi over 6 and integrate the limacon from pi over 6 to pi over 2, and then add those two areas together to get our entire area that we need. Okay, so starting with our general equation for the area of a polar graph, we're going to plug in our two equations. Then what we want to do is square both those equations. So for the 3 sine theta, we get 9 sine squared theta. And expanding out 3 minus 3 sine theta, we get 9 minus 18 sine theta plus 9 sine squared theta. Now when you go to integrate something that's like sine squared, you have to use your power reducing formulas. So we're going to rewrite the sine squared of theta as 1 minus cosine 2 theta over 2. And I did that in both equations. Then we're going to simplify that. So I really have 9/2 minus 9/2 cosine 2 theta. And the same thing happens over here on this equation. Notice that we do have the correct endpoints of integration on here. For this circle, we're going from 0 to pi over 6. And for the limacon, we're going from pi over 6 to pi over 2. Okay, this is where we left off. So for our next step, what we're going to do is go ahead and integrate these. So we have 9/2 becomes 9/2 theta. For the cosine of 2 theta, we make an adjustment of 1/2, and the integral of the cosine is the sine. So we have the sine of 2 theta. And then for this one, we have 9 theta. When we integrate 9, the integral of the sine is a negative cosine, so we had to change our sign here. And then we have 9/2 theta minus 9/2, and again that adjustment of 1/2 because we have twice the angle, and then we have the sine of 2 theta. Simplifying some more, we get 9/2 times 1/2 is 9/4 here. On this side I combine the 9 theta and the 9/2 theta to become 27/2 theta. And we had 9/2 times 1/2, which gives us 9/4. Okay, so now what we want to do is plug in our endpoints of integration. So where I have theta, I'm going to put in pi over 6 on this one. So I have pi over 6 here and pi over 6 here. And then I could go ahead and put in 0, but if you have 9/2 times 0, you would get 0. And also, if you put in a 0 here, you have 2 times 0, which is 0, and the sine of 0 is 0. So there won't be anything subtracted on this one. Now for the other one, we have 27/2 times pi over 2, 18 cosine of pi over 2, minus 9/4 sine of 2 times pi over 2. All that's going to be multiplied by 1/2 also. Now what we also want to do is go through and plug in pi over 6. So we're going to subtract that out. So we have 27/2 times pi over 6, but we're going to subtract it. We're going to subtract the 18 cosine of pi over 6, and we're going to add the 9/4 sine of 2 times pi over 6. And then we need to simplify that some more. So looking at this first one, we've got 9/2 times pi over 6, and then I'm going to multiply that by 1/2 and put everything in lowest terms. So that gives me 3 pi over 8. I'm also going to distribute the 1/2 to the 9/4 sine of 2 pi over 6, which simplifies to pi over 3. So that gives me 9/8 times the sine of pi over 3. Then I'm going to add 1/2 of the 27/2 times pi over 2, which simplifies down to 27 pi over 8. Then we're going to take 1/2 of the 18, which gives us 9, and cosine of pi over 2. And the 1/2 distributed to the 9/4 is 9/8. Crossing out the 2's, we get pi. For this term, we're going to get 27 pi over 2 times 2 times 6, which simplifies down to 9 pi over 8. And then for the next one, we have 1/2 times the 18, which is 9 cosine pi over 6. And our last term is 1/2 times 9/4, which gives us 9/8, and our angle simplifies down to pi over 3. Alright, the next step is to go ahead and combine all your pi terms. So we have 3 pi over 8, we have 27 pi over 8, and we have a negative 9 pi over 8, which comes out to 21 pi over 8. For the sine of pi over 3, we get square root of 3 over 2. For the cosine of pi over 2, we get 0. And for the sine of pi, we get 0. Then for the cosine of pi over 6, it's square root of 3 over 2. And the sine of pi over 3 is square root of 3 over 2. So we can reduce a little bit more. So we've got our pi's already. So we have all these square root of 3 over 2 terms, and notice that the first one and the last one here are canceling each other. So we just have minus 9 times the square root of 3 over 2. So this would be our exact answer for that area. And if you want to, you can estimate it. So it's 0.45 approximately for our area. Okay, thank you for tuning in to Demystifying Math.